Hi everyone. In this video we begin our discussion of determinants. The determinant of a matrix is just a scalar value, and it's something that we can compute from the entries of a matrix. It can tell us an awful lot about a ton of different things. Basically, anytime we have a square matrix involved in some kind of problem or application, there is always an interpretation of the determinant that is useful or insightful in some way. So a couple of things just to get us started. One is to know that every square matrix has a determinant, and only square matrices have determinants. Now, computation of the determinant is sometimes easy, sometimes hard. It kind of depends on exactly what case you're working in. But for 1 by 1 and 2 by 2 matrices, it's really easy. So to compute the determinant of a 1 by 1, right, a 1 by 1 matrix is really just something that looks like this. So 1 row, 1 column, that means only 1 entry. So if we have a matrix A that has just this one entry, a 1 by 1 matrix, then the determinant of A, which can be written as det A, or it can be written like this, or even like this. And the value of the determinant is just the entry A itself. Computing the determinant of a 2 by 2 matrix is only slightly more complicated. So let's take our favorite generic 2 by 2 matrix, A, B, C, D. The determinant of this matrix, det A, or if you like, we can write it like this, is just the value we get when we perform the following computation. So if we wanted to compute the determinant of, say, 2, 7, 1, 1, we can do that by just multiplying 2 times 1 and subtracting 7 times 1. And that's equal to -5. Now, we've seen this quantity before when we were computing the inverse of a 2 by 2 matrix. So let's just do that for this matrix B. B is 2, 7, 1, 1. What is B inverse? Well, if you recall, we computed B inverse by taking 1 divided by that exact 2 times 1 minus 7 times 1, and then multiplying that scalar quantity by a kind of scrambled up matrix. So the inverse of this matrix B is just -1 over 5, 7/5, minus 1 over -5, so that's 1/5, and 2 over -5, so that's minus 2/5. And this quantity right here, that is the determinant of matrix B. So often we'll see when we write down the formula for the inverse of a matrix, we'll write something like this. A inverse is equal to 1 over det A times D minus B minus C A. So we know that this scalar multiplier in the computation of the inverse of a 2 by 2 matrix is 1 over the determinant of that matrix. So if the determinant of A is equal to 0, then this scalar coefficient that we're trying to multiply by, well, that doesn't even exist. Right? We can't divide by 0. So if the determinant of A is equal to 0, then A inverse doesn't exist. And if A inverse doesn't exist, what does that tell us about the solutions to the linear system that has A as its coefficient matrix? Right, so let's remember that context. If AX equals B and A inverse doesn't exist, well, that means that that system either has no solution or it has infinitely many solutions. Now, one more thing that the determinant equaling 0 tells us about a matrix is that its columns, when considered as vectors, form a linearly dependent set. So that's a little bit about determinants in the 2 by 2 case. In the next video, we're going to talk about determinants of 3 by 3 matrices and see how to compute them.